Welcome back. In this lecture, we'll be discussing how to do analysis of the columns, long columns, on the basis of Euler buckling theory. So Euler buckling theory has been already discussed in the previous two videos, Euler and Rankine, and in this one we'll be discussing how to practically apply them. So now we know that the like this is one kind of a numerical problem. In this one we have a column of a section which is rectangular in section, and it has a dimensions of 15 centimeter by 20 centimeter. It has a dimension of 15 centimeter by 20 centimeter. This is the dimensions of this column, and this column is 6 meter long with both ends being fixed. So the boundary condition is very important. It is fixed, and you know what will be the effective length will be. The Young's modulus is given to you. What you have to define? You have to determine the critical load, and you have to define the safe load. What will be the safe load that can be applied on this column if the FOS, or the factor of safety, is given as 3. We'll be discussing what exactly factor of safety is. So now the crippling load, or the critical load P, as you can see, is equals to pi square EI upon L square, where L is the effective length. Now this is fixed from both the sides. So what is the condition for fixed? The condition is for fixed is it's like this. Rotations are not allowed, so effective length will be only half. So the effective L effective will be L by 2. Effective will be L by 2. You will be multiplying this with a factor of 1 by 2. So your L effective is equals to 1 by 2. You can put it here. Further, pi you know, E you know. E is 17.5. You can convert them and you can put it here. This is known. Now what is I? I is the, what is I for you? It's very important here. Here is the overall length is 6 meters. So 6 meters by 2 meters. So this will be 6,000 by 2. So this will be around 3,000 mm. Okay, so this will be the length. Okay, now we'll be discussing about what will be the I. Now as you can see, this is the rectangular cross section. So this is along XX and this is along YY. So you have to, with the expression of BD cube by 12, obtain IXX, and this is 15 cross 20 cube by 12, 15 BD cube by 12. So this comes out to be 10 to the power, how much? 1, 2, 3, 4 and 4. So 10 to the power 8 mm to the power 4. And the IYY will come out to be, this will be 20 times 15 cube by 12. So this will come out to be 5624 times 10 to the power 4 mm. So now you can see that IYY is less than IXX. So the column will tend to buckle in along IYY. The column will tends to buckle in YY direction. Now from the length of this column, this is very obvious. As you can see, along the YY only I have put in the buckling condition. Will not buckle along the XX. Definitely it will buckle, but this conditions will be attracted only through the moment of inertia, because we know that there are struts also. Okay, they are columns of very long shape and do not requiring only the fixed is along the earth only, along the that is along the direction of the earth. So that is also not justified here. So it's very important that you should be looking towards the moment of inertia, and the column which tends to buckle along the least moment of inertia, the buckling will occur along that direction only. So the critical load P will be, you can put that particular load pi square into 117.5 times 5625 10 to the power 4 divided by 3000, and so the overall, this will be equal to, this is square, so this will be equal to 1079 kilonewtons. So this is the critical load, this is the critical load at which the buckling will start. This is the critical load at which the buckling will start. But in the industrial conditions, what people used to do, they don't take it the theoretical values. They use some factor known as factor of safety to safely reduce the critical load. So with respect to factor of safety, the safe load that is experienced during the practical condition is basically the crippling load or the critical load divided by the factor of safety, which is, I think in this problem is given as 3. So this is actually the load, or the critical load is further reduced. This is approximately equals to 360 kilonewtons. So at 360 kilonewtons, see how much the load has now reduced. So at around 360 kilonewtons, you will be, this is the safe load, and you can operate your mechanism, you can operate your structures at this 360 load. You have also seen that while digging the earth for some purposes, like for digging for the water, or for digging a well of certain structure, or a pump, or any such conditions, we used to have a machine that requires a particular kind of load. So with the amount of vibrations that the machine has, we require certain amount of load so that the digging can take place. This is the machine that used to dig the earth, and it used to dig the earth in a very cylinder form. That means it takes up only the amount of, it digs like this, only takes up the earth's material only for the shape of the pipe only. So it is very cylinder condition only, it is for you. So in that case, the safe load for the machine, so that the structure do not fail, so that the machine do not fail itself, is around 360 after taking the factor of safety. Okay, so I hope you understand this problem. It's a very simple basic problem. In a similar way, these problems can be changed depending upon the type of boundary condition we may be having, or depending upon the cross-sectional area. So the important thing is, check out the L effective, then check out the moment of inertia in both the conditions, xx and yy, and check out that in which case the xx or yy is lower, that, and take that one, the lower moment of inertia, take that, the moment the column will buckle along that condition, and then you can calculate the critical load for the column. So now consider this example. This is one of the example of a simply supported beam. Simply supported beam. So in this case, what happens, this is a beam of length 4 meters, which is actually running a UDL of 30 kilonewtons per meter over the whole span, and it produces a deflection, in fact a central deflection of 15 mm at the center. Okay, so determine the crippling load or critical load when this beam is used as a column. When this beam is used as a column, what will be the critical load occurring on this beam? This beam as a whole will be used as a column somewhere. So what will be the critical load one will require if it has this boundary condition, one end fixed and other end hinged? If such boundary condition is there, one end fixed and other end hinged. So for such boundary condition, our effective length is, this is the one end fixed, and other end hinged. So in that case, this case, my L effective will be equal to 1 by root 2. One end fixed and other end hinged. So my L effective will be L by root 2. Okay, so one end fixed and in the other case both end pinned. That means both end pinned in both the conditions. That means the L effective will be equal to the L in this case that we have. So in the first case, my L effective will be equal to L by root 2. Okay, first thing. And this will be used as this beam will be used as a column. So I would, and there is no E given to me, there is no moment of inertia, all these things are not given. So let me check out the expression for the critical load. The critical load is actually pi square times EI upon LE effective square. This is my expression for the critical load. And if I see the expression for the deflection, now this is my deflection for a beam which is having a UDL. So deflection, we used to put the deflection as Y also, we used to put the deflection as delta also, all these things. So the deflection case for a simply supported beam with a UDL over its whole length, we have seen in one of the videos that it is equal to 5 upon 384 times W into L to the power 4 upon EI. W into L to the power 4 upon EI. This we have already seen in one of the videos where I have derived the expression through Castigliano's theorem. Delta equals to 5 upon 384 W L to the power 4. This is W. W is the running length of the L to the power 4 upon EI. So in this case, this is a deflection. Now the deflection is given to me 15 mm. This is given to me. And 584 is also 384. 5 upon 384 is a constant. W is given to me, and W is approximately 30 Newton per mm. Okay. Then what is there required? L. L is 4 meters. So this is 4000 to the power 4. So we can find it out in terms of EI. We can find the expression in terms of EI. We can put the values of EI here. And the effective length we know. We can replace it by this 1 upon root 2 square. So this will be 2 times pi square. And then on that basis we can obtain the critical load. I hope you are understanding what I'm trying to say here. So if you obtain the EI here, we'll be getting the EI as something as 2 by 3, 10 to the power 13 Newton mm square. And you can put these values here. So your crippling load in this case will be 2 pi square times EI by LE square, where actual length is 4000. So you can replace them by these things and you'll be getting 8224.5 kilonewton. Now the important thing is, you know how to calculate all these things. The important thing is here how a beam problem has been converted into a problem of column. This is important. So this is what it is. That means the beam here has been now converted to a column, and how you have obtained the critical load. Further, there is one more condition where both ends is pinned. So you can very easily do it. You know now that for the pinned condition, as we have seen earlier, for the pinned condition, both the ends are pinned. We have our L effective is equal to L. So in that case, for the second case, my L effective will be equal to L. That is 4000 mm, and so my critical load comes out to be 4112.25 kilonewtons. So these are only the theoretical value. Important thing is you should be understanding what has happened. As a numerical problem, what has happened is important to understand. So now we'll be doing one more problem, a very, very interesting problem. Further, I will not like to go into the details of this, but further problems may be categorized in, as you know, that it's the critical load is what is the important thing in a long column is. So you can play a problem. A person who's giving the problem can play up with the effective lengths by making the different end conditions, boundary conditions, or the second thing what he can do is by changing the different structures that can be used as a column. So I will be different for them, and how to calculate these i's. Like you may be given a problem of I section. Given a problem of I section, so you must be knowing like I section is like this. So you must be knowing how to obtain the moment of inertia of the I section. So once you'll be knowing how to do that, so you know how to obtain the moment of inertia. So obtain the moment of inertia for this I section. So this is a rectangular dimensions. This is like this. You might have seen this in railway tracks. This type of I sections are available, in which the rail actually is to run on these sections. So these type of I sections are available for the railway tracks. So some other columns also, some other conditions, some houses also, this such types of I sections are there. So what will be the moment of inertia of such sections? So the moment of inertia will be along x-axis, along this y, and maybe along this x-axis. So you have to find the moment of inertia along both these axes, because you know that we need to obtain the moment of inertia for along the least one. So to obtain the least one, you have to find the moment of inertia of the two sections. So now moment of inertia for this section, for this section, for this section, you have to find and obtain them overall, and then make a decision on the moment of inertia. So, and then the second thing is obtain the just check out the conditions. What is the conditions you may be experiencing? So L effective will be based on that. Okay. So like in this case, the moment of inertia here is Ixx will be moment of inertia of the rectangle of this rectangle 20 times 40. So this rectangle minus the moment of inertia of the rectangle of dimensions these two. So these two you will minus, and then you'll obtain the moment of inertia along the x-axis direction. Similarly, for the y direction, what you have to do to find out the moment of inertia for this one along the thickness times that one, and then you have to add the moment of inertia of the two rectangles. Okay, this length times this rectangle. So you have to add the moment of inertia of this. So in this way you have to find the moment of inertia for the I section. You can see different examples on internet and obtain how to obtain the. I hope you must be knowing, because in the first year engineering mechanics you must be knowing how to obtain the moment of inertia. Moment of inertia is to be obtained in those classes. So I hope you must be knowing how to obtain the moment of inertia. Similarly, the moment of inertia may be different for some may be another kind of a section known as T section. So there may be a T section like this, having a different moment of inertia. Once you will be knowing how to obtain the moment of inertia, whatever the section it is not exactly a T, but just consider it as a T. So for this section, you must be knowing how to obtain the moment of inertia. So in such type of problems will be given to you, and you know that only an examiner can play up in the effective length and the moment of inertia. These two things he may be given to you. He may also play up with E. So he might be giving you the stresses or the strains may be given to you, and you need to obtain the modulus in that case. So I request you to go through all these things and just practice how to obtain the moment of inertia of such section, T sections, and the flanges. There are some cases the flanges are also there. So just try to obtain the moment of inertia and try to know how this moment of inertia should be obtained, and then again the moment of inertia along the x-axis and the along the y and the x-axis can be compared, and then you can easily take the lowest moment of inertia, the one that is showing the least one. Now let's see this problem in which we have a case in which we have an external internal diameter of a hollow cast iron column. This is a hollow cast iron column having an internal diameter and external diameter. The internal is 4 cm, external 5 cm. If the length of this column is 3 meters and both of its ends are fixed, determine the crippling load. That means both the ends are fixed. L effective can be obtained from this fixed length. So now determine the crippling load required using the Rankine formula. Take the values of sigma c, that is crushing stress, as 550 Newton per mm square. Further, there is one more thing given, before we do this numerical, let's obtain something. Let's simplify the expression for the Rankine formula, expression from the Rankine formula. Now we know that the Rankine formula is 1 upon P is equal to 1 upon Pc crushing stress plus 1 upon Pe. Okay, now this can be rearranged as Pe plus Pc by Pc Pe. Okay, now we can take the reciprocal of both of them, so P becomes equal to Pc dot Pe, and further this can be written as Pe plus Pc. This can be further inserted as by dividing the numerator and denominator by Pe. So Pc upon 1 plus Pc by Pe. This can be further written as, just a moment, this battery is about to, just a moment, let me check it out. Okay, now it's okay. So this Pc, 1 plus Pc upon Pe. So now you can put the values of Pc and Pe. You can put the values. So this can be in terms of sigma c times A divided by 1 plus sigma c times A divided by pi square Ei upon Le square. K is the radius of gyration, you know. So now this can be further arranged by using the expression for the radius of gyration, and this can be further arranged as, okay, we can arrange this as sigma c dot A 1 plus sigma c dot A dot Le square divided by pi square E dot AK square, and this can be further rearranged to produce the expression sigma c dot A divided by 1 plus A times LC divided by K, LE divided by K square. So now this A is equal to sigma c pi square E. This A is a constant known as Rankine constant. This A is a constant known as Rankine constant. Now with the help of this constant, you can very easily, this constant may be given to you in most of the cases, because Rankine has obtained its constant for different values of iron. For wrought iron, he has obtained the crushing stress and the corresponding A. You can obtain the crushing stress basically. So similarly for cast iron also. So as a material constant, this can be used, and you can directly use the expression for the critical load here, sigma c dot A 1 plus A Le by K. So most of the time, in case of a Rankine expression, we use this type of expression to obtain the critical load. So in this problem also we'll be using the same one. So if both the side of the cylinder is fixed, we have been given A as equals to 1 upon 1600. This ratio is given to us as A is given to us as 1 by 1600 ratio. So this is what all the, let's remove this. Now let's come out to exactly the numerical what we have to solve. So now we know that the external diameter D is 5 centimeter to us, and small d the internal is 4 centimeter. We can obtain the area as 225 pi, okay, mm square, and we can obtain moment of inertia I as pi by 64. Outer minus inner, so 5 4 minus 4 4, so you can obtain this as 57 656 pi mm. We'll all convert to them as an mm, and then since we require the radius of gyration also, k also is required here, so let's calculate k, square root of I minimum. Now it's a circular cross section, so I will be same, no minimum will be there, so this will be 25.625 mm. Length is 3000, that means 3 meters, and both end is fixed, so L effective is equals to L by 2 for case of both lengths fixed, so this is 1500 mm, 1500, sorry. Okay, crushing stress is 550, A is given 1600, so use this expression to obtain the critical load. So by using this expression we can obtain the critical load as 550 times 225 pi, okay, and divided by 1 plus A is 1600, 1 by 1600 times 1500 divided by 25.625, which is k, square of this. So this will lead to 123,750 Newton, something like that. So the important thing is to acknowledge this fact that the expression, the empirical expression that we have used for the Rankine formula can be now reduced to a simpler, more simpler expression, considering in terms of critical load for any type of column. Okay, it may be a short column, it can be a long column, in any type of column which requires a crushing load, okay, and a effective length with respect to radius of gyration. So LE by K here, what does it becomes? LE by K, I have to tell you something. LE by K, let's come here. LE by K is a cylinderness ratio. So that is what he is trying to do. He is trying to tell you the expression for the the cylinderness ratio is kind of again squarely related to it. Okay, it's inversely proportional to the critical load of the structure. So this can be said as a square of the cylinderness ratio, and this is A is a Rankine constant. So in this way, again, as I said, the expression has been now made a bit of with putting different values, the expression is made like this. So now again you can be tested with different kinds of boundary condition, and the way you have to obtain the moment of inertia. That means IXS or IYY. The way you obtain the moment of inertia and the way you obtain the boundary condition, with respect to boundary condition, what will be the effective length. So in these two cases you will be tested. So I request you to do some of the numerical problems, and with the end of this we'll be giving you some of the numerical problems, numerical sheets, kind of a tutorial to you, so that will be having a more idea of how to do these problems. So the important thing that I would like to tell you, the approach, how should you be approaching the problem. Whatever the kind of problem given to you, just ensure that the kind of formula that is required in that, it's a small column or a large column, short column or a large column, and then see the types of boundary condition it is using, okay. And the another thing is the moment of inertia, because the least of the one you have to take away. So I think this is enough for the column. I think these 3 videos of columns would have been a bit of knowledgeable to you, and we'll be looking towards to wipe up this section as quickly as possible. There are many questions that used to come for the gate examination also, and I require here to tell you about these things. Mostly the problems that used to come is in terms of different boundary conditions that are experienced by the different columns. So you need to remember these types of different boundary conditions to yourself. Okay, so I hope this video would be informative to you. Okay, thank you.